Good evening and welcome back. Tonight we're exploring one of the most controversial and captivating mysteries of the ancient world. The Pyramids of Giza and the Great Sphinx, monuments that have stood silent for millennia, guarding secrets that may challenge everything we thought we knew about human history. Get cozy, settle in, and let's begin. Stand before the Great Pyramid of Giza, and you're looking at approximately 2,300,000 blocks of stone, some weighing as much as 70 tons. Beside it crouches the Sphinx, weathered and enigmatic, its lion body stretching 73 meters across the desert sand. For generations, we've been told these structures were built around 2,500 years before the Common Era, tombs for pharaohs, constructed by workers using copper tools and wooden sledges. But what if that story is incomplete? What if these monuments are not merely 4,500 years old, but reach back into a time we barely understand? What if they encode knowledge of astronomy, mathematics, and earth sciences that shouldn't exist in the historical period we've assigned them? This is the question that has driven Graham Hancock, a British author and journalist, to spend more than 3 decades investigating what he calls a forgotten chapter in human civilization. Hancock isn't an archaeologist by training. He studied sociology at Durham University and spent years as a respected journalist for publications including The Economist, The Times, and The Guardian. But his work has taken him down paths that few academics dare to tread, proposing theories that challenge the very foundations of our understanding of ancient history. Hancock's central thesis is both simple and revolutionary. He argues that an advanced civilization flourished during the last ice age, roughly 12,000 years ago, possessing sophisticated knowledge of astronomy, mathematics, and engineering. This civilization, he proposes, was largely destroyed in a global catastrophe around 10,800 years before the Common Era, an event that coincides with the period known as the Younger Dryas. The survivors of this cataclysm, Hancock suggests, traveled the world, sharing their knowledge with hunter-gatherer communities and helping to spark the rise of civilizations in places like Egypt, Mesopotamia, and Mesoamerica. The pyramids and the Sphinx, in Hancock's view, are not merely monuments built by ancient Egyptians. They are repositories of knowledge, encoded messages from a lost civilization, warnings and wisdom preserved in stone for future generations to discover. Some elements of these structures, he argues, particularly the Sphinx, may date back to that lost civilization itself, making them far older than mainstream archaeology acknowledges. These are extraordinary claims, and they have made Hancock one of the most controversial figures in the world of ancient history. Mainstream archaeologists have labeled his work pseudoscience, dismissed his theories as fantasy, and accused him of cherry-picking evidence to fit a predetermined conclusion. Yet Hancock's books have sold millions of copies worldwide. His Netflix series Ancient Apocalypse has been viewed by tens of millions, and his appearances on podcasts like The Joe Rogan Experience regularly attract audiences in the millions. Why do these ideas resonate so powerfully? Perhaps because they touch something deep within us, a sense that our history is longer and stranger than we've been told. Perhaps because the mysteries Hancock points to are real, the questions he asks are legitimate, even if his answers remain controversial. Or perhaps because in an age when we've mapped the genome and sent probes to the edge of the solar system, there's something deeply appealing about the idea that our own past still holds secrets waiting to be uncovered. The story of the pyramids and the Sphinx has always been a story of mystery. Even in ancient times, these monuments inspired awe and speculation. The Greek historian Herodotus, writing in the 5th century before the Common Era, described the Great Pyramid as one of the wonders of the world and recorded what the Egyptian priests told him about its construction. Though scholars debate how accurate those accounts were, for centuries the pyramids captured the imagination of travelers and scholars. Medieval Arab historians proposed that they were built before the biblical flood to preserve knowledge. European explorers in the Renaissance era measured them obsessively, seeking hidden meanings in their dimensions. In the 19th century, the rise of Egyptology as a scientific discipline brought more systematic study, but also more questions. The conventional archaeological narrative tells us that the pyramids were built during Egypt's 4th dynasty, around 2,550 years before the Common Era. The Great Pyramid, also known as the Pyramid of Khufu or Cheops, is attributed to Pharaoh Khufu. The second pyramid is attributed to his son Khafre, who is also credited with carving the Great Sphinx. The third and smallest of the three main pyramids was built by Khafre's successor, Menkaure. This dating is based on several lines of evidence. Archaeological excavations have uncovered workers' villages near the pyramids, revealing the lives of the people who presumably built them. Hieroglyphic inscriptions in chambers and passages reference the pharaohs. Carbon dating of organic materials found in the pyramids, such as wood and reeds used in mortar, generally supports dates in the range of 2500 to 2600 years before the Common Era. The conventional explanation for how the pyramids were built involves massive labor forces, estimated at anywhere from 20,000 to 100,000 workers, using ramps to haul the massive stone blocks into place. The precision of the construction, the alignment with cardinal directions, and the internal passages and chambers are all explained as the result of advanced planning, skilled craftsmanship, and the accumulated engineering knowledge of the Old Kingdom period. But this narrative, Hancock argues, leaves too many questions unanswered. How did workers using copper tools, which are softer than the granite used in some parts of the pyramids, achieve such precision? How were blocks weighing 70 tons or more lifted and positioned with accuracy measured in millimeters? Why do the pyramids align with such extraordinary precision to true north, within a fraction of a degree? And why, if these were merely tombs, were no mummies or substantial funerary goods ever found in the main chambers? Even more puzzling is the question of knowledge. The dimensions of the Great Pyramid, when analyzed in certain ways, appear to encode sophisticated mathematical constants and astronomical information. The structure's proportions closely approximate the mathematical constant pi in the ratio of its height to its base perimeter. Certain measurements yield values near the golden ratio, phi. Hancock and others have suggested that its location on the Earth's surface was deliberately chosen, though this geographic claim remains highly debated among researchers. These are not simple coincidences, Hancock argues. They represent knowledge, a legacy from a civilization that understood the Earth, the heavens, and mathematics in ways that challenge our assumptions about the capabilities of ancient peoples. And nowhere is this challenge more apparent than in the weathered face of the Sphinx. The Great Sphinx of Giza is one of the world's most recognizable monuments. Carved from a single outcrop of limestone, it sits on the Giza Plateau with its head facing due east toward the rising sun. Its body measures 73 meters in length, and the head rises 20 meters above the desert floor. For centuries, the Sphinx was buried up to its neck in sand, only occasionally excavated for brief periods before the desert reclaimed it. Conventional archaeology dates the Sphinx to the reign of Pharaoh Khafre, around 2,500 years before the Common Era, contemporary with the construction of the Second Pyramid. This dating is based largely on stylistic arguments, the resemblance of the Sphinx's face to known statues of Khafre, and its proximity to Khafre's pyramid and valley temple. But in the early 1990s, a Boston University geologist named Robert Schoch made an observation that would ignite one of the fiercest debates in modern archaeology. Schoch, invited by writer John Anthony West to examine the Sphinx from a geological perspective, noticed something unusual about the erosion patterns on the monument's body and the walls of the enclosure in which it sits. The Sphinx and its enclosure display deep, undulating erosion patterns, vertical fissures and channels that cut into the limestone. This type of weathering, Schoch argued, is characteristic of prolonged exposure to heavy rainfall, not the wind and sand erosion you would expect in Egypt's arid climate. The challenge with this interpretation is that Egypt hasn't experienced sustained heavy rainfall for thousands of years. The last time the Giza region enjoyed a climate wet enough to produce such erosion, according to geological records, was at the end of the African humid period, which concluded around 7,000 to 5,000 years before the Common Era, and before that, during the wetter conditions at the end of the last ice age. Based on his geological analysis, Schoch concluded the Sphinx must be much older than the conventional dating. His initial estimate suggested the core body of the Sphinx could date to somewhere between 7,000 and 5,000 years before the Common Era, making it at least twice as old as the conventional date. Schoch has since suggested it could be even older, though he's been careful to present this as geological interpretation rather than definitive proof. Graham Hancock, working with engineer Robert Bauval, took Schoch's geological findings and integrated them into a broader theory. In their book, The Message of the Sphinx, published in 1996, Hancock and Bauval proposed a more specific and dramatic timeline. They argued that the Sphinx could have been carved around 10,500 years before the Common Era, during the epoch that ancient Egyptians called Zep Tepe, meaning the first time, a primordial age referenced in ancient texts as the beginning of Egyptian civilization. This date goes considerably beyond what Schoch's geological analysis suggested, representing Hancock and Bauval's interpretation of both geological and astronomical evidence combined. This dating, Hancock and Bauval noted, aligns perfectly with an astronomical phenomenon. Due to the slow wobble of the Earth's axis, known as precession of the equinoxes, the constellation that rises on the eastern horizon at the spring equinox changes over time, cycling through all 12 zodiac constellations over a period of approximately 25,920 years. Around 10,500 years before the Common Era, at the spring equinox, the constellation Leo would have been rising on the eastern horizon at dawn. The Sphinx, with its lion's body, faces due east. At that moment in time, 10,500 years before the Common Era, it would have been gazing directly at its celestial counterpart, the constellation Leo, at the moment of the spring equinox sunrise. This alignment, Hancock and Bauval argue, is too precise to be coincidental. In their interpretation, it represents an intentional marking of that specific epoch, a monument designed to commemorate Zep Tepe, the first time. However, critics have noted that the constellation Leo, as we define it today, is a Greek construct, and there's no clear evidence that ancient Egyptians of 10,500 years before the Common Era would have recognized the same star pattern as a lion. There's another curious detail that some researchers believe supports the idea that the Sphinx is much older than conventionally dated. The head of the Sphinx is noticeably small in proportion to its massive body. If you compare the Sphinx to other Egyptian statuary, the proportions appear unusual. This observation has led some researchers to propose that the head we see today is not the original. Rather, they suggest, the current head, which does appear to resemble representations of Pharaoh Khafre, was recarved from a much larger original head at some point in antiquity. This remains a hypothesis, however, debated among researchers who study the monument. If this is true, it would explain why the head shows much less weathering than the body. The recarved head would have been exposed to the elements for a much shorter period than the body. It would also explain the disproportionate size. The original head, perhaps carved as a lion's head to match the lion body, would have been larger and more in proportion. When it was recarved, perhaps during the 4th dynasty when Khafre renovated or repaired the Sphinx, the sculptors had to work with what remained of the original stone, resulting in the smaller, out-of-proportion head we see today. Critics of the water erosion hypothesis have offered alternative explanations. Some geologists have argued that the erosion patterns could be the result of other factors, such as wind-blown sand mixed with dew or moisture that condenses on the stone during cooler nights, a phenomenon that can occur even in arid climates. Others have pointed out that different layers of limestone weather at different rates, and the Sphinx, carved from stratified limestone, shows varying degrees of erosion in different areas. The debate over the Sphinx's age remains unresolved. Most mainstream Egyptologists continue to date it to the 4th dynasty, arguing that the archaeological and historical evidence linking it to Khafre is compelling despite the geological questions. But the water erosion hypothesis refuses to go away. It's been featured in numerous documentaries, debated in academic papers, and remains one of the most intriguing mysteries surrounding the Giza monuments. For Hancock, the evidence of the Sphinx's great age is part of a larger pattern. The monument is not just an ancient statue, it's a marker, a deliberate pointer to a time when, he believes, a sophisticated civilization flourished on Earth. And that civilization, he argues, left other clues encoded in the very layout of the Giza Plateau itself. If you look at the 3 main pyramids of Giza from above, you notice something curious. They are not arranged in a straight line. The 3rd and smallest pyramid is offset slightly to the east of the line formed by the other 2. For years, this offset was explained as a quirk of the terrain. Perhaps the builders couldn't place the 3rd pyramid exactly in line because of the underlying bedrock. But in 1983, Robert Bauval, a Belgian-born engineer working in Saudi Arabia, had an epiphany. Looking up at the stars of Orion's belt one night, he noticed something familiar. The 3 stars that form Orion's belt, Al-Nitak, Al-Nilam, and Mintaka, are not arranged in a perfect straight line. The third star, Mintaka, is offset to the east, just like the third pyramid at Giza. Bauval began to investigate. The more he looked, the more the correlations seemed compelling. The relative positions of the three pyramids, their sizes relative to each other, and even their orientations match remarkably well with the three stars of Orion's belt. The smallest pyramid corresponds to the dimmest star, Mintaka. The middle pyramid, slightly smaller than the Great Pyramid, corresponds to Al-Nilam, and the Great Pyramid corresponds to Al-Nitak, the brightest of the three belt stars. This became known as the Orion Correlation Theory, and Bauval first published it in 1989 in the journal Discussions in Egyptology. He later expanded on the theory in collaboration with Adrian Gilbert in the book The Orion Mystery in Forcris, 1994, and with Graham Hancock in Keeper of Genesis, published as The Message of the Sphinx in the United States. In 1996, the theory goes deeper than just the layout of the pyramids. The ancient Egyptians had a profound connection to the constellation Orion. In their mythology, Orion was associated with Osiris, the god of death and resurrection, one of the most important deities in the Egyptian pantheon. The constellation Sirius, which sits below Orion in the sky, was associated with Isis, Osiris's sister and wife. The ancient Egyptians believed that the pharaohs would journey to Orion after death, joining with Osiris in the afterlife. The pyramid texts, ancient funerary inscriptions found in pyramids from the Old Kingdom period, contain numerous references to Orion and the deceased king's journey to the stars. "O king, you are this great star, the companion of Orion, who traverses the sky with Orion," one text reads. These weren't just poetic metaphors, Bauval argues. They were literal descriptions of a belief system that saw the pyramids as earthly representations of stellar destinations. But there's more. Inside the Great Pyramid, there are four narrow shafts that extend from two chambers, the King's Chamber and the Queen's Chamber below it. For years, these shafts were assumed to be ventilation shafts, though this never made much sense, since the shafts from the Queen's Chamber don't actually open to the outside, and ventilating a tomb seems unnecessary. Bauval proposed a different interpretation. Using astronomical software to model the night sky as it appeared over Giza in different epochs, he found that around 2,500 years before the Common Era, roughly the time the pyramids were conventionally dated to have been built, the southern shaft from the King's Chamber pointed in the direction of Al-Nitak, the star in Orion's belt that corresponds to the Great Pyramid. The southern shaft from the Queen's Chamber pointed toward Sirius. In Bauval's view, these weren't ventilation shafts, but symbolic passageways for the pharaoh's soul to ascend to the stars, precisely aligned to the most important stellar destinations in Egyptian theology. The correlation wasn't perfect due to the slow drift of stellar positions over time caused by precession. Though Bauval argued the alignment was close enough to demonstrate intentional design, Hancock embraced Bauval's Orion Correlation Theory and wove it into his broader narrative about a lost civilization. If the layout of Giza represents the stars of Orion, Hancock asked, what epoch does it represent? Using computer simulations of the sky, Hancock and Bauval examined how the stars of Orion's belt would have appeared at different points in history. Due to precession of the equinoxes, the angle at which Orion's belt rises above the horizon changes over the millennia. They found that the alignment between the ground layout at Giza and the stars of Orion's belt was not best for 2,500 years, before the Common Era, the conventional date of the pyramids. Instead, the correlation was most precise for the epoch around 10,500 years before the Common Era, the same date suggested by the Sphinx water erosion hypothesis, and the same epoch when Leo was rising at the spring equinox. This led Hancock and Bauval to propose that the Giza layout is a kind of time map, a message from an ancient civilization marking the epoch of Zep Tepe. The pyramids themselves may have been built during the 4th dynasty, but the site plan, the carefully chosen layout that mirrors the stars, may have been laid out much earlier, perhaps by survivors of the lost civilization who wanted to preserve the memory of their world and the catastrophe that destroyed it. The Orion Correlation Theory sparked intense debate. Astronomers raised questions about the precision of the correlation. Ed Krupp of the Griffith Observatory in Los Angeles and Tony Farrell of the University of Cape Town independently examined the theory using planetarium equipment. They found that the angle between the three belt stars and true north in 10,500 years before the Common Era was approximately 47 to 50 degrees, while the angle formed by the three pyramids measures approximately 38 degrees. This represents a discrepancy that critics argued was too large to support claims of precise correlation. Additionally, Krupp noted that if you inverted the star map to match the ground layout, which Bauval and Hancock had done in presenting the correlation, you still had to account for this angular difference. Hancock and Bauval countered that the critics were being overly precise in their measurements, and that small discrepancies didn't invalidate the broader pattern. They also pointed out that the pyramids had suffered damage and alteration over millennia, which could affect precise measurements. The debate reached a peak in 1999, when the BBC's flagship science program, Horizon, or AR, aired a documentary titled Atlantis Reborn that was highly critical of Hancock and Bauval's theories. The program featured the astronomical criticisms and included a segment where they showed that you could create correlations between star patterns and earthly landmarks for almost any arrangement if you were selective enough about which points you included. They demonstrated this by mapping the constellation Leo onto famous New York City landmarks, arguing that Hancock and Bauval were engaging in pattern finding that wasn't scientifically rigorous. Hancock and Bauval filed complaints with the Broadcasting Standards Commission, arguing that the program had been unfair and had omitted their rebuttals to the astronomical criticisms. After a year of deliberation, the commission upheld one part of their complaint, ruling that the program had unfairly omitted Hancock and Bauval's detailed responses to the specific astronomical criticisms. The BBC broadcast a revised version of the documentary in 2000, but it still maintained serious skepticism about the theories. Despite the controversy, the Orion Correlation Theory captured public imagination in a way that few archaeological theories have. It suggested that the ancient Egyptians, or whoever laid out the Giza site, possessed sophisticated astronomical knowledge and were encoding messages in their monuments, messages that spanned not just the landscape but also vast stretches of time. For Hancock, this astronomical encoding was evidence of something profound. A civilization that thought in terms of vast celestial cycles, that understood the slow precession of the equinoxes taking 25,920 years to complete, and that built monuments designed to last through the ages, must have been thinking on a timescale and with a level of knowledge that challenges our assumptions about ancient peoples. And the encoding, Hancock argues, goes even deeper when you examine the mathematics and measurements of the pyramids themselves. The Great Pyramid is not just big, it's precisely big. Its original height was 146.6 meters, though the top 30 meters are now missing. Its base covers an area of 13 acres, with each side originally measuring approximately 230.4 meters. The four sides are aligned to the cardinal directions, north, south, east, and west. With an accuracy that is extraordinary, the maximum error is less than 1/20th of a degree. These measurements have fascinated researchers for centuries because they seem to encode mathematical constants and relationships. One of the most discussed is the relationship involving pi. The mathematical constant pi, approximately 3.14159, describes the relationship between a circle's circumference and its diameter. It's a transcendental number, infinite and non-repeating in its decimal expansion, and it shows up throughout mathematics in the natural world. If you take the height of the Great Pyramid and divide it into the perimeter of its base, you get a number very close to 2 times pi. This could mean the builders deliberately incorporated pi into the pyramid's design, though some researchers have shown that this relationship can arise naturally if you build a pyramid using certain geometric methods involving circles, even without knowing the precise value of pi. The ancient Egyptians did use rough approximations for circular measurements in their surviving mathematical papyri, though these don't match the precision seemingly encoded in the Great Pyramid's proportions. Hancock and other researchers have pointed out that the pyramid also incorporates the golden ratio, phi, approximately 1.618. The golden ratio appears throughout nature and has fascinated mathematicians and artists for millennia because of its aesthetically pleasing properties. In the Great Pyramid, if you take the slant height of one face, the distance from the base to the apex along the face's surface, and divide it by half the base length, you get a number very close to the golden ratio. These mathematical relationships, Hancock argues, are not accidental. They represent sophisticated knowledge encoded in stone. But there's more. The dimensions of the Great Pyramid, when properly scaled, appear to encode information about the Earth itself. Graham Hancock frequently draws attention to what he sees as a fascinating numerical relationship. In his analysis, if you take the height of the Great Pyramid and multiply it by 43,200, you get a number very close to the polar radius of the Earth. If you take the base perimeter of the pyramid and multiply it by the same constant, 43,200, you get a number very close to the Earth's equatorial circumference. Hancock emphasizes this as potential evidence of encoded knowledge. Why 43,200? This number, Hancock notes, appears in various ancient timekeeping systems. It relates to the precessional cycle, the slow wobble of Earth's axis that takes approximately 25,920 years to complete. 43,200 is 1/6 of 25,920, and various factors of these numbers appear in Sumerian, Babylonian, and Hindu calendrical and astronomical systems. Critics have pointed out several problems with these numerical relationships. First, the original dimensions of the Great Pyramid are not known with absolute precision. The outer casing stones, which would have defined the exact measurements, have largely been removed over the centuries. The measurements we do have, mostly from the detailed survey conducted by Sir Flinders Petrie in 1883, show some variation between the different sides of the pyramid, likely due to erosion, settling, and damage over millennia. Second, the Earth itself is not a perfect sphere. Its polar radius and equatorial radius differ by about 21 kilometers due to the planet's rotation causing an equatorial bulge. When Hancock and others talk about the pyramid encoding Earth's dimensions, which measurement are they using? The answer varies. Sometimes it's the polar radius, sometimes the equatorial, and sometimes an average or mean radius, depending on which gives the closest match to the pyramid's proportions multiplied by the chosen constant. Third, and perhaps most damning, the critics argue that if you're free to choose any scaling constant you like, and you're working with measurements that have a range of uncertainty, and the target you're trying to match also has a range of values, you can create apparent correlations that don't really mean anything. It's a form of numerology, pattern finding in numbers that looks impressive, but doesn't necessarily represent intentional encoding of information by the ancient builders. Hancock has responded to these criticisms by arguing that the critics are being overly pedantic. The ancient builders didn't need to know the Earth's dimensions to 15 decimal places to be demonstrating advanced knowledge. If they had a general understanding of the Earth's shape and size, and they encoded that understanding in a monument using a scaling constant that relates to astronomical cycles they clearly knew about, that's still remarkable even if it's not perfect to modern standards of precision. The debate over mathematical encoding in the pyramids mirrors larger debates about how we should interpret ancient monuments. Are we seeing intentional messages and sophisticated knowledge, or are we projecting our own modern understandings onto structures that were built with different purposes and different ways of thinking? What's undeniable is that the Great Pyramid's alignment to true north is extraordinarily precise, accurate to within about 3 arc minutes, or 1/20th of a degree. This level of precision would have required careful astronomical observations and sophisticated surveying techniques. The builders clearly possessed advanced knowledge of astronomy and geometry. The question is how advanced and what other knowledge they may have possessed. For Hancock, the mathematical relationships in the Great Pyramid are part of a broader pattern of encoded knowledge that he believes was inherited from an earlier, lost civilization that had a sophisticated understanding of mathematics, astronomy, and the Earth itself. This brings us to the core of Hancock's hypothesis, his proposal that such a civilization once existed and that its destruction shaped the course of human history. Graham Hancock's central claim is audacious. He proposes that during the last ice age, roughly between 15,000 and 11,500 years before the Common Era, an advanced human civilization flourished somewhere on Earth. This civilization, he argues, possessed knowledge of astronomy, mathematics, navigation, agriculture, and monumental architecture. They had explored and mapped large portions of the planet. They understood complex astronomical phenomena like the precession of the equinoxes, They built sophisticated structures and developed technologies that allowed them to thrive in Ice Age conditions. Then, approximately 12,800 years ago, catastrophe struck. A series of massive comet fragments slammed into the Earth's ice sheets, primarily in North America and possibly in other locations around the globe. The impacts caused unimaginable destruction, triggering massive wildfires, generating enormous quantities of dust and debris that darkened the skies, and most significantly, melting vast amounts of ice that caused sea levels to rise catastrophically and brought on a period of global cooling known as the Younger Dryas. This is not entirely speculation. Noun Dryas. The Younger Dryas is a well-established climatic event. Around 12,800 years ago, the Earth, which had been warming steadily as it emerged from the last ice age, suddenly plunged back into near-glacial conditions for approximately 1,300 years. The Younger Dryas ended abruptly around 11,500 years ago, and the Earth resumed its warming trend. What caused the Younger Dryas has been debated by scientists for decades. The mainstream explanation involves changes in ocean circulation patterns, particularly the shutdown of the Atlantic meridional overturning circulation due to massive freshwater input from melting ice sheets. In 2007, however, a group of researchers proposed an alternative explanation, that the Younger Dryas was triggered by a cosmic impact event. The Younger Dryas impact hypothesis points to several lines of evidence. At sites across North America, Europe, and elsewhere, proponents identify a distinct layer in the geological record dated to the beginning of the Younger Dryas that they claim contains unusual materials. Elevated concentrations of platinum and other elements, rare on Earth, but common in asteroids and comets. Nanodiamonds, they argue, formed under the extreme heat and pressure of an impact event. Magnetic spherules, carbon-rich layers indicating widespread fires, and melt glass. This hypothesis has generated considerable scientific debate, with many researchers challenging the interpretation of the evidence and noting that no definitive impact crater from this period has been identified. This hypothesis remains controversial within the scientific community. Many researchers have challenged the interpretation of the evidence, arguing that the materials found in the Younger Dryas boundary layer could have other explanations and that no definitive impact crater from this period has been identified. However, proponents of the hypothesis, including scientists from respected institutions, continue to publish research supporting the impact scenario, and in recent years, there have been reports of a possible impact structure beneath the Greenland ice sheet that might date to this period. Hancock embraced the Younger Dryas impact hypothesis because it provided a mechanism for the catastrophe he believes destroyed his hypothesized Ice Age civilization. The impacts would have caused immediate devastation in the regions where they struck. The subsequent climate changes, flooding from rapidly melting ice and sea level rise, followed by the cold snap of the Younger Dryas, would have made vast areas uninhabitable and would have caused crop failures, famine, and societal collapse for any advanced civilization that existed at the time. In Hancock's scenario, a small number of survivors from this civilization escaped the destruction. They had knowledge, skills, and memories of a more advanced world, and they traveled to different parts of the globe, seeking refuge among scattered groups of hunter-gatherers who had survived the catastrophe. These survivors, whom Hancock sometimes refers to as the magicians, shared their knowledge, teaching agriculture, architecture, and astronomy to the societies they encountered. This, Hancock argues, explains the sudden rise of civilization in various parts of the world, beginning around 11,000 to 10,000 years ago. Sites like Göbekli Tepe in southeastern Turkey, with its massive stone pillars and complex carvings dated to around 9,600 years before the Common Era, appear to show a sudden leap in architectural sophistication with no apparent precursors. Similar patterns can be seen in the rapid development of agriculture in the Fertile Crescent, the rise of early civilizations in Egypt and Mesopotamia, and the sophisticated astronomical knowledge apparent in later cultures. Göbekli Tepe deserves special attention in Hancock's narrative because it represents what he sees as compelling evidence for his theories. Discovered in the 1990s by German archaeologist Klaus Schmidt, Göbekli Tepe consists of massive circular structures built from T-shaped limestone pillars, some weighing 10 tons or more. These pillars are carved with intricate reliefs of animals, abstract symbols, and geometric patterns. Archaeological dating places the site at approximately 9,600 years before the Common Era, making it older than Stonehenge by more than 6,000 years, and older than the pyramids by more than 6,500 years. What makes Göbekli Tepe so remarkable is that it was built during a period when people in the Pool region were transitioning from mobile hunter-gatherer lifestyles. According to conventional archaeological understanding, monumental architecture typically emerges after the agricultural revolution, after people settle in permanent communities and develop the surplus resources and social organization necessary to undertake large construction projects. Göbekli Tepe appears to challenge this sequence. For Hancock, this pattern makes sense if you accept his hypothesis. The builders weren't starting from scratch, but were influenced by survivors of an earlier catastrophe who possessed knowledge of stoneworking and monumental construction. The astronomical significance of Göbekli Tepe also interests Hancock. Some researchers have proposed that the arrangement of the pillars and the carvings on them might encode astronomical information, possibly relating to constellations and the positions of celestial bodies at specific times. These interpretations remain speculative and debated within the archaeological community. If such astronomical encoding could be demonstrated, however, it would parallel what Hancock sees at Giza: monuments designed to preserve and transmit astronomical data from particular epochs. The carved animals at Göbekli Tepe, which include lions, foxes, wild boar, snakes, and various birds, might represent constellations. The overall layout of the circular structures might represent a kind of astronomical observatory or calendar. While these interpretations remain debated, they fit into Hancock's broader pattern of ancient sites being designed to preserve and transmit astronomical knowledge. Flood myths represent another line of evidence that Hancock emphasizes. Virtually every culture on Earth has traditions of a great flood that destroyed an earlier world. The biblical flood of Noah, the Mesopotamian flood in the Epic of Gilgamesh, the Greek flood of Deucalion, the Hindu flood of Manu, various flood stories among Native American tribes, Australian Aboriginal traditions about rising seas, Polynesian tales of floods and drowned lands. The catalogue is extensive. Mainstream scholars generally interpret these flood myths in several ways: as memories of local flooding events, which would have been catastrophic to small ancient communities, as symbolic narratives about creation, destruction, and renewal, or as independent developments of similar archetypal stories. But Hancock raises the question: could these stories preserve genuine memories of the flooding that occurred at the end of the Ice Age when sea levels rose by over 100 meters? Could they be distorted historical accounts passed down through oral tradition for thousands of years, rather than pure mythology? The timing would be right. The most dramatic sea level rise occurred between 15,000 and 7,000 years ago, with particularly rapid rises during meltwater pulses when massive amounts of ice melted quickly. One of the most significant pulses occurred around 11,600 years ago, at the end of the Younger Dryas, when temperatures rose sharply and ice sheets collapsed. Coastal settlements would have been inundated, islands would have disappeared beneath the waves, river valleys would have flooded. For people living through these events, it would indeed have seemed like the world was drowning. If Hancock's Ice Age civilization was primarily coastal, as he proposes, located on the continental shelves that were exposed during the Ice Age when sea levels were much lower, then the flooding at the end of the Ice Age would have been absolutely catastrophic to them. Their cities, their ports, their centers of culture and knowledge would have been drowned, submerged beneath hundreds of feet of water. The survivors fleeing inland would have carried memories of this catastrophe, stories that became the flood myths we find across world cultures. This interpretation of flood myths as historical rather than purely symbolic is controversial. Mainstream scholars point out that oral traditions can't preserve accurate information over thousands of years without writing systems. They argue that the similarities between flood myths might reflect common human experiences of flooding rather than a single global event. And they note that flood myths aren't actually universal. Some cultures don't have them at all. But Hancock counters that we shouldn't underestimate the power of oral tradition. Australian Aboriginal traditions, preserved through song cycles and dreaming stories, appear to contain accurate geographical information about coastlines and landscapes that existed thousands of years ago when sea levels were lower. Similar arguments have been made for Native American oral traditions. If these traditions can preserve some accurate information over millennia, why couldn't flood myths preserve memories of actual catastrophic flooding? The Younger Dryas itself provides physical evidence of dramatic climate change at exactly the time Hancock's theory requires. The climate record from ice cores shows a sudden plunge into near-glacial conditions around 12,800 years ago, followed by 1,300 years of cold, and then an equally sudden warming around 11,500 years ago. This wasn't a gradual change. The temperature shifts happened over decades, perhaps even faster in some regions. What caused these rapid changes is the subject of ongoing scientific debate. The impact hypothesis proposes that comet fragments struck the ice sheets, causing massive melting that disrupted ocean circulation patterns and triggered rapid cooling. Critics of this hypothesis argue that the evidence is ambiguous and that the traditional explanation involving changes in ocean currents is sufficient. But proponents continue to find supporting evidence, including impact markers in sediment cores, melt glass, and now possibly impact structures. For Hancock, the Younger Dryas represents the window when his hypothesized civilization was destroyed. The initial impacts caused immediate destruction. The climate chaos that followed made large areas uninhabitable. The flooding from melting ice drowned coastal settlements. By the time the Younger Dryas ended and conditions stabilized, the Ice Age civilization was gone, erased except for the knowledge preserved by survivors and the stories that became myths. The survivors of the lost civilization, Hancock proposes, encoded their knowledge and warnings in monuments designed to last through the ages. The pyramids and the Sphinx at Giza, various megalithic sites around the world, and ancient myths and flood stories found in cultures across the globe are all part of this legacy. They're trying to tell us something, Hancock argues. They're warning us that catastrophe can strike from the skies, that civilizations can fall, and that we should pay attention to the cosmos and prepare for the possibility of future impacts. Critics of Hancock's lost civilization hypothesis raise several fundamental objections. First and foremost, they ask, where is the archaeological evidence? If an advanced civilization existed during the Ice Age, where are the cities, the tools, the garbage dumps, the countless material remains that civilizations leave behind? Hancock has spent decades searching, and while he points to anomalies and suggestive sites, he hasn't found a smoking gun, a clear, unambiguous settlement or artifact that proves his Ice Age civilization existed. Hancock's response is that most of the evidence was destroyed in the catastrophe, or lies buried under hundreds of feet of sediment deposited during the flooding at the end of the Ice Age, or submerged under the ocean, drowned when sea levels rose by approximately 120 meters as the Ice Age ice sheets melted. He argues that we've barely begun to explore the continental shelves where coastlines existed during the Ice Age, and that's where the main centers of his lost civilization would have been located. The second objection is about methodology. Critics argue that Hancock cherry-picks evidence that fits his theory while ignoring contradictory evidence. They point out that he relies heavily on diffusionist arguments, suggesting that similarities between distant cultures must be due to contact or a common source, rather than independent development, or the fact that humans everywhere face similar challenges and sometimes arrive at similar solutions. The third objection concerns his use of astronomical arguments. Critics note that if you can choose the date you're trying to prove, and you have the flexibility to select which astronomical alignments matter and which measurements to emphasize, you can create the appearance of significant correlations where none really exist. The constellations of the zodiac, they note, are human constructs, patterns we impose on random arrangements of stars, and those constructions originated in Mesopotamia and were unknown in Egypt until much later. Hancock acknowledges that his theories remain unproven. He doesn't claim to have definitive evidence of his lost civilization. What he claims is that there are enough anomalies, enough puzzling features in the archaeological and geological record to warrant serious investigation. He argues that mainstream archaeology has been too quick to dismiss evidence that doesn't fit the conventional narrative and too resistant to considering alternative timelines for human development. The debate is fierce, and it reveals deeper tensions in how we study the past. Mainstream archaeologists emphasize the importance of careful excavation, peer-reviewed analysis, and the slow accumulation of evidence. They're wary of grand theories that outrun the evidence, and they're particularly concerned about theories that suggest ancient peoples needed help from lost civilizations or aliens to build their monuments, seeing this as demeaning to the real achievements of ancient cultures. Hancock, for his part, argues that he's not trying to diminish ancient achievements. He's trying to expand our understanding of how old and sophisticated human civilization might be. He sees himself as asking questions that need to be asked, even if they make academics uncomfortable. And he points out that he's encouraged more investigation, more research into sites like Göbekli Tepe and underwater archaeology than might otherwise have occurred, even if his specific theories turn out to be wrong. Whatever the truth about a lost Ice Age civilization, Hancock's work has undeniably focused attention on genuine mysteries about the pyramids and the Sphinx. And nowhere are those mysteries more apparent than in the question of how these massive structures were actually built. Ask an Egyptologist how the pyramids were built, and you'll likely hear about ramps, lots and lots of ramps. The standard theory is that workers dragged massive stone blocks up long, gradually sloping ramps that wound around or stretched straight up the sides of the growing pyramid. As the pyramid got taller, the ramps got longer or higher. When the pyramid was finished, the ramps were dismantled, leaving no trace. It sounds plausible until you examine the details. The Great Pyramid contains approximately 2,300,000 stone blocks. If it was built during the 23-year reign of Pharaoh Khufu, as conventional chronology suggests, workers would have had to place a block every 2 to 3 minutes, working around the clock, every single day for more than 2 decades. Even if we allow that work happened only during certain seasons or daylight hours, the pace of construction required is staggering. The blocks themselves present challenges. The core blocks average 2.5 tons each, roughly the weight of a large automobile. But some blocks, particularly those used in the king's chamber and other internal chambers, weigh much more. The granite beams forming the ceiling of the king's chamber weigh an estimated 50 to 80 tons each. They were quarried in Aswan, about 800 kilometers up the Nile, transported to Giza, and lifted to a height of over 40 meters above ground level with millimeter precision. Then there's the precision of the construction. The base of the Great Pyramid is leveled to within 2.1 centimeters across its entire 230-meter width. The sides are aligned to the cardinal directions with extraordinary accuracy. The internal passages and chambers are built with blocks fitted so precisely that you can't slip a knife blade between them. Some of the granite blocks in the king's chamber weigh dozens of tons, yet are cut and positioned with such accuracy that the walls are perfectly flat and meet at precise 90-degree angles. Copper tools, which were the hardest metal available to the Old Kingdom Egyptians, are softer than the granite used in parts of the pyramids. You cannot effectively cut granite with copper. Modern experiments have shown that you can make shallow scratches or grooves with copper tools, aided by abrasive sand, but cutting the massive granite beams found in the pyramids would have taken an impractical amount of time and destroyed countless tools. Some researchers have proposed that the ancient Egyptians possessed lost techniques, perhaps involving different types of tools or methods we don't yet understand. There are theories about using wet wooden wedges to split stone, though this doesn't explain the precision cutting. There are theories about using sand, water, and copper saws in a grinding process, though again, the time required seems impractical. Some have even proposed that the Egyptians used a form of concrete, creating the blocks by pouring a mixture rather than carving them, though chemical analysis has generally not supported this idea. The ramp theory has its own problems. A straight ramp leading to the top of the Great Pyramid would need to be well over a kilometer long to maintain a reasonable gradient. Such a ramp would contain more material than the pyramid itself. A spiral ramp winding around the pyramid could be shorter, but it would obscure the corners of the pyramid during construction, making it difficult to maintain the precision of the angles and alignments. In recent years, French architect Jean-Pierre Houdin proposed an intriguing alternative, an internal ramp. Houdin's theory suggests that after the lowest portions of the pyramid were built using a short external ramp, workers constructed a spiraling ramp inside the pyramid, within the mass of the structure itself. Blocks could be hauled up this internal ramp to the higher levels. The theory is based on careful analysis of the pyramid's structure and some anomalies visible in scans of the interior. Houdin's internal ramp theory has gained attention because it addresses some of the problems with external ramp theories, but it remains controversial and unproven. The only way to verify it would be to conduct extensive internal surveys or excavations, which Egyptian authorities have been reluctant to permit. The challenges of constructing the internal chambers are even more perplexing than moving the blocks themselves. The king's chamber, located deep within the pyramid, is constructed from enormous granite beams. 9 massive beams form the ceiling, with individual beams estimated to weigh between 25 and 70 tons. Above this chamber are 5 more chambers, separated by additional granite beams, creating a complex stress-relieving structure that has successfully supported the weight of hundreds of thousands of tons of stone for over 4,000 years. How were these beams, quarried at Aswan, 800 kilometers away, transported to Giza? The conventional answer involves floating them down the Nile on barges during the annual flood season when water levels were high. But even granting that this was possible, how were they then moved from the river to the construction site and lifted to a height of over 40 meters above ground level? And how were they positioned with such precision that the chamber's walls meet at perfect 90-degree angles and the ceiling is level? The tolerances achieved in the king's chamber are remarkable even by modern standards. The walls are flat to within fractions of a millimeter. The blocks fit together so tightly that you cannot insert a knife blade between them. The chamber is perfectly rectangular. This level of precision working with granite, one of the hardest stones, using supposedly primitive copper tools, strikes many researchers as implausible. Some have suggested that the ancient Egyptians possessed harder tools than we've found evidence for, perhaps steel or even diamond-tipped implements, though no such tools have been discovered in archaeological contexts from the Old Kingdom. Others propose that they used extremely patient grinding techniques, spending years cutting each block. Still, others suggest sound or vibration techniques, though there's no evidence for this and it's unclear how such methods would work in practice. The precision extends to the pyramid's exterior as well. The original casing stones, most of which were removed in medieval times to build structures in Cairo, were cut and fitted with extraordinary accuracy. The remaining casing stones at the base of the pyramid show surfaces polished to near mirror smoothness, with joints between stones so tight that they're barely visible. Each casing stone weighed several tons, yet they were shaped and positioned with precision measured in millimeters. The alignment of the Great Pyramid to true north, accurate to within 3 to 4 arc minutes, is another achievement that speaks to sophisticated knowledge. True north is not the same as magnetic north, which varies depending on local magnetic anomalies. Finding true north requires astronomical observations, specifically observing the circumpolar stars that never set below the horizon and determining the exact point around which they appear to rotate. Several methods have been proposed for how the ancient Egyptians achieved this alignment. One involves observing the rising and setting positions of a star on the eastern and western horizons, marking those positions and bisecting the angle between them to find true north. Another involves using a plumb line and water to level a circular trench, then observing the reflection of stars in the water. Whatever method was used, it required careful observation, mathematical calculation, and precision execution. The base of the Great Pyramid is another marvel. The foundation is level to within 2.1 centimeters across its 230-meter width, despite being built on bedrock that was not naturally level. This means the builders either cut the bedrock to create a level surface or built up lower areas to match higher areas, achieving extraordinary levelness in either case. The 4 sides of the base are equal in length to within a few centimeters, forming an almost perfect square covering 13 acres. Modern surveying can achieve such precision easily, but how did the ancient Egyptians do it with the tools available to them? They would have needed to establish a perfectly level baseline, then extend that level across the entire site, then mark out a square with sides of equal length and perfect 90-degree corners. Each of these steps is challenging when working at this scale, and the cumulative precision achieved is remarkable. Water leveling has been proposed as one method. By creating channels or trenches and filling them with water, you can establish a level reference line since water always seeks its own level. This could work for establishing levelness, though it doesn't explain the precision of the square layout and the alignment to cardinal directions. Some researchers have proposed that the ancient Egyptians had more sophisticated surveying instruments than we've found. Evidence 4. There are hints in Egyptian art of measuring tools, including what appear to be plumb bobs and leveling tools. but nothing that obviously explains the precision achieved in the pyramids. It's possible that wooden or other perishable surveying instruments existed but haven't survived in the archaeological record. For Hancock, the construction mysteries are part of a larger pattern, suggesting that we don't fully understand the capabilities of the ancient builders, or perhaps that the pyramids involved input from people with more advanced knowledge than we. Credit to the Old Kingdom Egyptians. He stops short of claiming aliens or levitation, as some fringe theorists do, but he does argue that the conventional explanations are incomplete, and that we should remain open to the possibility that the builders possessed sophisticated techniques or knowledge that has been lost. The logistics of the construction project are also mind-boggling. If the pyramid was built in 23 years, as conventional chronology suggests, and if work happened primarily during the flood season when agricultural labor was available, we're looking at perhaps 3 months of construction per year. That means the work had to progress even faster than the already astonishing rate of 1 block every 2 to 3 minutes. Even if we allow work during more of the year, the pace is extraordinary. The workforce would have been immense. Estimates range from 20,000 to 100,000 workers, depending on assumptions about construction methods and work schedules. These workers would have needed to be fed, housed, and organized. Recent archaeological discoveries of worker villages near the pyramids have provided evidence of how this was accomplished, showing bakeries, breweries, and housing for laborers. But coordinating such a massive workforce, maintaining discipline and quality control, ensuring accurate measurements and alignments, this required sophisticated project management that speaks to a high level of organizational ability. The quarrying of the stones presents its own mysteries. The bulk of the pyramid blocks are limestone quarried from the Giza Plateau itself. Evidence of quarrying can be seen in the landscape around the pyramids. But how exactly were blocks weighing 2.5 tons each cut from the bedrock using copper tools? Experimental archaeology has shown it's possible to cut limestone with copper tools, aided by abrasive sand and considerable patience. But the time required per block makes the construction timeline even more compressed. The granite used in the king's chamber and other internal structures came from Aswan, as mentioned. Granite is much harder than limestone and much more difficult to cut. Some researchers have noted that copper tools simply aren't hard enough to effectively cut granite. You'd spend more time making new tools than cutting stone. This has led to speculation about lost techniques, perhaps involving heating the rock and then rapidly cooling it to create cracks, or using very hard stone tools like dolerite pounders. Tool marks on some granite blocks show curved grooves that have puzzled researchers. If these grooves were made by copper saws using sand as an abrasive, the cutting rate implied by the depth and spacing of the marks is faster than modern experiments have achieved with replica tools. Some have argued this indicates some unknown technique or harder tools, while others suggest the marks might be from later repair work using iron or steel tools. The transportation of blocks within the construction site is another puzzle. Once blocks were cut and shaped, they had to be moved to their final positions. For the lower courses, this might have involved sledges on lubricated ground, with evidence suggesting water or milk was used to reduce friction. But for higher courses, blocks had to be raised, presumably up ramps. Moving a 2.5-ton block up a ramp with a reasonable gradient using only human muscle power and simple tools is possible but requires many workers and careful coordination. The fitting together of blocks raises additional questions. Many blocks throughout the pyramid are simply stacked with rough joints, but in critical areas like chambers and passages, the blocks are cut and fitted with precision. This selective precision suggests that the builders knew where to invest extra effort for structural reasons and where rough work was sufficient. That engineering judgment speaks to sophisticated understanding of structural mechanics. The overall design of the pyramid, with its complex interior passages, chambers, and stress-relieving structures, represents remarkable architectural and engineering achievement. The system of corbelled passages and chambers distributes weight effectively. The 5 relieving chambers above the king's chamber have successfully prevented the collapse of the ceiling for over 4 millennia despite the enormous weight pressing down from above. This shows understanding of structural principles that wouldn't be formalized in engineering texts until much later. There's another mystery about the pyramids that Hancock emphasizes: the question of what they were actually for. The standard answer is that they were tombs, elaborate monuments to house the bodies and treasures of pharaohs in the afterlife. But this explanation faces some challenges. No mummy of Khufu has ever been found in the Great Pyramid, and the sarcophagus in the king's chamber stands empty, undecorated, and without a lid. This could mean the tomb was robbed in antiquity, as happened with many Egyptian burials. However, unlike the elaborately decorated tombs in the Valley of the Kings, which are covered in hieroglyphic inscriptions and colorful paintings depicting the pharaoh's journey through the afterlife, the main chambers in the Great Pyramid are notably stark and unadorned. The only inscriptions in the entire structure are some rough hieroglyphs in chambers above the king's chamber that were discovered by Colonel Howard Weiss in the 19th century. Those hieroglyphs, which include what appears to be a cartouche of Khufu, have themselves been the subject of debate. Some researchers have questioned their authenticity, suggesting they might have been painted by Weiss to validate his discoveries and secure his place in history. Hancock investigated these markings personally in the late 1990s and subsequently stated that he believes they are genuine, though debates about their authenticity continue in some alternative research circles. But even if Khufu's name is legitimately associated with the Great Pyramid, that doesn't necessarily prove it was his tomb. It could mean he renovated it, added to it, or claimed it in some way. There's an ancient artifact called the inventory stela found at Giza, which describes Khufu performing restoration work on the Sphinx, implying the Sphinx existed before Khufu's reign. Most Egyptologists date this stela to a much later period, possibly the 26th dynasty, more than 2,000 years after Khufu, and consider its historical claims unreliable or legendary rather than factual. However, some alternative researchers point to it as possible evidence of an earlier origin for the Giza monuments. Some researchers have proposed they were astronomical observatories, power plants, water pumps, or machines for focusing some kind of energy. The Grand Gallery in the Great Pyramid, with its corbelled walls and precise alignment, has been noted as an ideal location for observing stars as they cross the meridian, supporting the observatory theory. The sarcophagus in the king's chamber has unusual acoustic properties. If you strike it, it resonates with a deep tone. The chamber itself, built from granite which contains high amounts of quartz crystal, may have interesting acoustic or resonance properties. Some researchers have investigated whether the pyramid could have been designed to create or amplify certain frequencies for ritual purposes or some other function we don't understand. Hancock doesn't claim to know definitively what the pyramids were for, but he emphasizes that we shouldn't be too confident in the tomb theory given its significant gaps. He suggests that the pyramids might have served multiple purposes. Yes, they had symbolic and religious significance, and perhaps some funerary association, but they might also have been observatories, markers for astronomical alignments, and repositories of encoded knowledge about mathematics, astronomy, and the Earth itself. The idea that the pyramids encode knowledge, that they are, in effect, books written in stone, has a long pedigree. In the 19th century, some researchers claimed to find all sorts of prophecies and hidden meanings in the pyramids' measurements. Much of that work was numerology, finding patterns that weren't really there, or imposing interpretations that reflected the researchers' own beliefs rather than anything the original builders intended. But the fact that some people have made unfounded claims doesn't mean the pyramids don't contain genuine encoded information. The astronomical alignments of the shafts, the mathematical relationships in the proportions, the careful orientation to cardinal directions, these are real features of the structures that suggest intentional design beyond simply building a big pile of rocks as a tomb. For Hancock, the pyramids and the Sphinx together form a complex, a site carefully designed to transmit information across vast stretches of time. The Sphinx marks an astronomical epoch, 10,500 years before the Common Era through its orientation and the implied Leo alignment. The pyramids mark that same epoch through the Orion Correlation, and possibly encode information about the Earth's dimensions and astronomical cycles. Together, they point to Zep Tepe, the first time, an era that Hancock believes was the age of his lost civilization. The idea that ancient peoples would create monuments designed to last for millennia and to communicate with distant future generations is not as far-fetched as it might sound. Many cultures have been concerned with legacy, with passing knowledge to the future. The very act of building something as massive and durable as the pyramids suggests thinking on a grand timescale. And if you believed, as the survivors of a catastrophe might, that such disasters could recur, that future civilizations might face similar threats, You might indeed try to leave warnings, encoded in structures designed to outlast any written records. Whether Hancock is right about this or not, his work has focused attention on real questions. The Sphinx does show unusual erosion patterns that deserve explanation. The Orion correlation, whatever its ultimate significance, is a genuine pattern that exists in the layout of Giza. The mathematical relationships in the pyramid's proportions are there, even if we debate their meaning. These are not inventions. They're real features of real monuments, and they deserve serious study. And that brings us to the final aspect of Hancock's work, the fierce resistance he's encountered from the academic establishment, and what that tells us about how science approaches anomalous evidence. From the moment Hancock began publishing his theories in the 1990s, he has faced intense criticism from mainstream archaeologists and Egyptologists. He's been labeled a pseudoscientist, a fantasist, and worse. His work has been dismissed as not worthy of serious consideration by academic institutions. Archaeology departments warned students away from his books. When his Netflix series Ancient Apocalypse was released in 2022, it prompted an open letter from the Society for American Archaeology asking Netflix to reclassify the show as science fiction rather than documentary. The criticisms of Hancock's work fall into several categories. First, methodological. Critics argue that he cherry-picks evidence, ignores contradictory data, and relies too heavily on arguments from ignorance, claiming that because mainstream science can't explain something, his alternative explanation must be correct. Second, evidentiary. They point out that he has no smoking gun, no clear archaeological evidence of his lost civilization, despite decades of searching. Third, theoretical. They argue that his diffusionist model, suggesting that cultural similarities are due to a common ancient source, is outdated and fails to credit independent human ingenuity. There's also a concern about the social impact of alternative archaeology. Some researchers worry that theories suggesting ancient peoples needed help from lost civilizations or aliens to build their monuments are inherently disrespectful to the real achievements of ancient cultures. They're particularly sensitive to this in regions where colonial powers historically dismissed indigenous accomplishments. Hancock has responded to these criticisms vigorously. He argues that he's not claiming ancient peoples were incapable or needed alien help. He's suggesting that some ancient peoples had help from other ancient peoples, specifically survivors of his proposed Ice Age civilization who had preserved advanced knowledge. He sees nothing demeaning in this. Rather, he's arguing for a longer, more sophisticated history of human achievement. On the methodological criticisms, Hancock acknowledges that he doesn't have definitive proof of his lost civilization, but argues that he's raising legitimate questions about anomalies in the archaeological record. He points out that mainstream archaeology has its own biases and has been wrong before about when and how various developments occurred. The date for the peopling of the Americas has been pushed back repeatedly as new evidence emerges. Sites like Göbekli Tepe have forced reconsideration of when monumental architecture began. Science progresses by questioning accepted theories, Hancock argues, and his questions are worth considering even if his specific answers turn out to be incorrect. The documentary War with the BBC in 1999 and 2000 was particularly revealing. The original Atlantis Reborn program on Horizon presented Hancock and Bauval's theories and then subjected them to severe criticism, particularly focusing on the astronomical issues with the Orion Correlation Theory. Hancock and Bauval felt that the program had been unfair, specifically that it had filmed their detailed rebuttals to the astronomical criticisms, but then didn't air those rebuttals, making it appear as though they had no response to the critiques. The Broadcasting Standards Commission ultimately agreed that the program had been unfair on that specific point. The BBC broadcast a revised version, though the revised program still maintained significant skepticism about Hancock and Bauval's theories. The incident became a cause célèbre in the alternative history community, seen as an example of establishment bias against unconventional ideas. More recently, the debate has continued in new venues. Hancock has made numerous appearances on the Joe Rogan Experience podcast, where he's been able to present his ideas at length to audiences of millions. His Netflix series, Ancient Apocalypse, was watched by tens of millions of viewers worldwide. Meanwhile, archaeologists have increasingly used social media, YouTube, and podcasts to present rebuttals and explain why they find Hancock's theories unconvincing. The Netflix series in particular sparked an intense new round of debate. Ancient Apocalypse, released in late 2022, presented Hancock's theories with high production values, dramatic cinematography, and persuasive narration. It became one of Netflix's most-watched documentary series, but it also drew fierce criticism from professional archaeologists, who felt it presented speculative theories as established fact, and gave a platform to ideas that lack scientific consensus. The Society for American Archaeology issued an open letter expressing concern about how the series presented archaeological claims, worried that viewers might not distinguish between Hancock's interpretations and mainstream archaeological understanding. Several archaeology organizations in other countries issued similar statements. The reaction revealed deeper tensions about how scientific knowledge is communicated to the public in the age of streaming media and social media. Traditional academic publishing reaches small audiences and takes years. Popular media can reach millions in days. If controversial theories gain mass audiences while scholarly rebuttals remain confined to academic journals, how does the public evaluate competing claims? Hancock responded to the criticism vigorously, arguing that he'd been transparent about his theories being controversial, and that he was raising legitimate questions that deserved investigation. He accused some critics of wanting to silence alternative viewpoints and of being protective of academic orthodoxy. He pointed out that he'd never claimed his theories were proven, only that they deserved serious consideration. The debate also highlighted questions about expertise and who gets to interpret the past. Hancock is not a credentialed archaeologist, but he's spent decades studying ancient sites, reading archaeological reports, and interviewing researchers. Does his lack of formal credentials mean his observations are invalid? Or can an intelligent layperson, especially one who's devoted his career to the subject, offer valuable insights that credentialed experts might miss? Mainstream archaeologists generally argue that expertise matters. Archaeology is a complex discipline requiring training in excavation techniques, artifact analysis, dating methods, and theoretical frameworks. Amateur enthusiasts, no matter how passionate, can misinterpret evidence or miss crucial context that professionals would recognize. Moreover, the discipline has ethical responsibilities to the communities whose heritage they study and to preserving irreplaceable archaeological sites and artifacts. But Hancock and his supporters counter that expertise can also lead to tunnel vision, that professionals invested in current theories might be resistant to evidence that challenges those theories. They point to cases in history where outsiders or maverick thinkers made important discoveries that the establishment initially rejected. They argue for intellectual humility and openness to alternative hypotheses, even unconventional ones. One interesting development is that some aspects of Hancock's broader narrative are becoming less controversial. The Younger Dryas impact hypothesis, which Hancock has championed, has gained more support from researchers, even if it remains debated. The idea that there may have been sophisticated cultures in the Americas much earlier than previously thought has gained support from new archaeological finds. The recognition that hunter-gatherer societies could create monumental architecture, as at Göbekli Tepe, has changed assumptions about what's possible in pre-agricultural societies. Specific archaeological critiques of Hancock's work have focused on several key issues. Regarding the Sphinx water erosion hypothesis, geologists who've examined the monument have offered alternative explanations for the erosion patterns. They've pointed to chemical weathering from dew and moisture condensing on the limestone, differential weathering of different stone layers, and subsurface water seeping through the rock. They note that not all geologists who've examined the Sphinx agree with Schoch's interpretation of water erosion from rainfall. On the Orion Correlation Theory, astronomers have noted that the alignment between the pyramids and Orion's belt is not as precise as Bauval and Hancock claimed, particularly for the epoch of 10,500 years before the Common Era that they emphasize. The discrepancy of nearly 10 degrees in the angle is significant. Moreover, critics point out that the constellations are human constructs. The ancient Egyptians didn't group stars into the same constellations that we recognize today, and there's no clear evidence they saw Orion's belt as we do. Regarding the mathematical encoding in the pyramids, critics have shown that when you have flexibility in choosing measurements, constants, and the relationships you're testing, you can create apparent correlations that don't represent intentional design. They've demonstrated this by finding similar encoded relationships in other structures that clearly weren't designed to encode such information. The presence of pi and phi in the pyramid's proportions might be the natural result of using certain geometric construction methods rather than deliberately encoding these constants. On the broader lost civilization hypothesis, the absence of clear archaeological evidence remains the strongest criticism. If an advanced civilization existed during the Ice Age, with knowledge of astronomy, mathematics, and monumental architecture, where are the cities, the tools, the pottery, the countless material remains that civilizations leave behind? Hancock's argument that most evidence was destroyed or submerged doesn't fully satisfy critics who note that archaeologists have found plenty of evidence of Ice Age human activity, including cave paintings, tools, and campsites, just nothing suggesting the kind of advanced civilization Hancock proposes. Dating methods also present challenges for Hancock's theories. Radiocarbon dating of organic materials in the pyramids, while not perfect, generally supports construction in the Old Kingdom period around 2,500 years before the Common Era. The hieroglyphic evidence, including inscriptions in internal chambers and graffiti left by work crews, all point to 4th dynasty dates. While Hancock has questioned the authenticity of some inscriptions, particularly the cartouches in the relieving chambers above the king's chamber, his own investigation led him to conclude they were genuine. The mainstream narrative also has evidence in its favor. Beyond just the absence of evidence for Hancock's alternative, we have detailed archaeological records of Egyptian civilization developing over time. We can trace the evolution of pyramid construction from early mastaba tombs to step pyramids to the smooth-sided pyramids at Giza to later pyramids. We have records of quarries, worker villages, tools, and the organizational apparatus of the Old Kingdom state. This evidence paints a picture of indigenous Egyptian development without needing to invoke a lost civilization. Yet the mainstream narrative also has gaps and unresolved questions. The rapid development of hieroglyphic writing and sophisticated art in the early dynastic period does seem relatively sudden. The organizational capacity required to build the pyramids does seem remarkable for a civilization supposedly just emerging from the Neolithic. The precision of construction and the mathematical relationships in the pyramids do seem to suggest knowledge beyond what we might expect. These gaps don't prove Hancock's alternative theory, but they do suggest our understanding remains incomplete. The debate also touches on broader questions about how science progresses and how we should handle unconventional theories. The scientific method emphasizes skepticism, peer review, and the accumulation of evidence. Extraordinary claims require extraordinary evidence, but science also progresses through challenges to accepted theories. Continental drift was dismissed by mainstream geologists for decades before becoming accepted. Meteorites were considered impossible before evidence became overwhelming. Many scientific revolutions began with observations that didn't fit current theories. How do we balance healthy skepticism with openness to new ideas? How do we encourage rigorous investigation while not dismissing evidence that doesn't fit current frameworks? These are not easy questions, and the Hancock controversy highlights the tensions involved. Some archaeologists have tried to engage constructively with the questions Hancock raises while rejecting his specific answers. They've pointed out that ancient peoples were remarkably clever and capable, that we shouldn't need to invoke lost civilizations or alien help to explain ancient achievements, but that we should also not underestimate what ancient peoples could accomplish. The pyramids are impressive precisely because they were built by people using the technology available at the time, not despite it. Other scholars have focused on improving public communication about archaeology, creating accessible content that explains how archaeologists work, what evidence they've found, and why they reach the conclusions they do. The goal is to help the public understand the difference between evidence-based archaeology and speculative alternative theories, while acknowledging that archaeology does have uncertainties and ongoing debates. Yet the core of Hancock's thesis, the Ice Age civilization itself, remains unproven and highly controversial, and the specific claims about the age of the Sphinx and the significance of the Giza layout remain contested. Critics point out that 30 years of searching has not produced the definitive evidence that would be needed to overturn the conventional chronology. Hancock's position is that the search has barely begun. The world's continental shelves, where he believes the main settlements of his lost civilization would have been located, remain largely unexplored. Underwater archaeology is expensive and difficult. Many countries restrict access to important sites. In Hancock's view, the lack of evidence is not evidence of absence. It's simply evidence that we haven't looked thoroughly enough in the right places. This is a difficult argument to counter or to prove. The principle that absence of evidence is not evidence of absence is valid in science. Many things that were once considered impossible or non-existent have turned out to be real when we finally had the tools and opportunity to detect them. On the other hand, you can't prove a negative, and if the evidence for something remains forever just beyond reach, always in the places we haven't yet searched, at some point the skepticism of the scientific community is justified. What seems clear is that the debate between Hancock and mainstream archaeology is unlikely to be resolved soon. Both sides have dug in. Hancock shows no signs of abandoning his quest, and mainstream archaeologists show no signs of embracing his theories. Perhaps the resolution will come from future discoveries, new technologies for exploring underwater sites or scanning beneath deserts, new dating methods, or new analytical techniques that can extract more information from existing evidence. In the meantime, the pyramids and the Sphinx remain, as they have for millennia, silent sentinels guarding their secrets. And that brings us to one of the most intriguing aspects of Hancock's theories, his search for the legendary Hall of Records. According to both ancient legends and modern psychic readings, specifically those of Edgar Cayce in the 1930s, there is supposed to be a hidden chamber beneath the Giza Plateau containing records from a lost civilization, potentially Atlantis in some tellings. This Hall of Records supposedly contains artifacts, texts, and technology from before the flood, preserved by survivors who foresaw the coming catastrophe. Hancock and Bauval, in The Message of the Sphinx, suggested that if such a chamber exists, its location might be encoded in the layout and alignments of the Giza monuments. Using the correlation between the layout and the sky in 10,500 years before the Common Era, they speculated about possible locations where such a chamber might be hidden. Several investigations have been conducted over the years to search for hidden chambers at Giza using ground-penetrating radar, seismic surveys, and other remote sensing techniques. Some of these have detected anomalies, possible voids in the bedrock beneath the plateau or within the pyramids themselves. In 2017, a major international project using cosmic ray muon detectors discovered a large void above the Grand Gallery in the Great Pyramid, a finding that generated worldwide headlines. However, Egyptian authorities have been cautious about invasive exploration, and the function or significance of these voids remains unclear. The search for the Hall of Records captures something essential about the appeal of Hancock's theories. It's the promise that there's more to discover, that beneath the sands or within the stones lie answers to fundamental questions about who we are and where we come from. Whether or not a literal Hall of Records exists, the idea that the ancient world has more secrets to reveal resonates deeply. If Hancock is even partially correct, if there was an earlier chapter in human civilization that has been forgotten, if the monuments at Giza are older or more sophisticated than we've believed, if they encode knowledge from a lost world, then our understanding of history needs to be revised in fundamental ways. We would need to reconsider not just the age of the pyramids and Sphinx, but our entire model of how civilization develops. The standard archaeological narrative describes civilization as emerging gradually over thousands of years, developing from hunter-gatherer bands to settled agricultural communities to towns and cities, and eventually to the complex state societies we see in ancient Egypt, Mesopotamia, and elsewhere. This development, in the mainstream view, happened independently in different regions, with occasional contact and influence but no single common source. If Hancock is right, this narrative would need to incorporate an earlier layer. A mother civilization that existed during the Ice Age, was destroyed in a catastrophe, and whose survivors seeded later civilizations with knowledge and techniques. This would fundamentally change how we think about cultural development, suggesting more continuity and transmission of knowledge across what we currently see as a major temporal gap. The implications would extend to multiple fields of study. Linguistics would need to consider whether language families might have deeper roots than currently recognized if survivors of a lost civilization spread across the world. Genetics would need to explain how populations moved and mixed during and after the Ice Age. Climate science would need to more fully explore the Younger Dryas and its causes. Astronomy would need to acknowledge that ancient peoples may have had more sophisticated understanding of celestial mechanics than is generally credited. It would also raise profound questions. Who were these Ice Age people? What was their society like? What technologies did they possess? The conventional view is that Ice Age humans were hunter-gatherers living in small bands, following animal migrations, making stone tools, creating cave art, but not building permanent structures or developing agriculture or writing. If Hancock is correct, at least some Ice Age populations went far beyond this, developing maritime capabilities, astronomical knowledge, architectural skills, and perhaps even early forms of writing or symbolic communication that haven't been recognized. What kind of society could have developed this knowledge during the challenging conditions of the Ice Age? The Ice Age climate was harsh in many regions, with extensive ice sheets covering northern latitudes, colder average temperatures, and lower sea levels exposing more land. But not all regions were equally affected. Some areas, particularly coastal regions that are now underwater, may have had relatively moderate climates and abundant marine resources that could support more complex societies. Maritime cultures focusing on ocean resources rather than agricultural land might have been the core of Hancock's Broder's hypothesized civilization. Coastal settlements would explain why we haven't found much evidence. They're now submerged beneath hundreds of feet of water. Maritime people would have developed navigation skills, boat-building technology, and knowledge of ocean currents and celestial navigation. They might have traded over vast distances, spreading knowledge and techniques between different regions. Such a civilization might have looked very different from the agricultural civilizations we're familiar with. Instead of large cities with monumental architecture, they might have had dispersed settlements connected by sea routes. Instead of vast agricultural fields, they might have relied on fishing, sea mammal hunting, and coastal gathering. Their material culture might have emphasized marine resources, shell tools, fishbone needles, materials that don't preserve well in the archaeological record. But if they had knowledge of astronomy and mathematics, if they could predict celestial cycles and understand Earth's dimensions, that suggests a level of intellectual development that goes beyond purely practical survival skills. This knowledge would require centuries or millennia of careful observation, record-keeping, and analysis. It would require some form of information storage and transmission, whether oral traditions, some form of notation, or mnemonic systems we haven't recognized. The catastrophe that Hancock believes destroyed this civilization would have been traumatic in ways difficult for us to comprehend. Imagine a world-spanning culture, however loose and dispersed, with accumulated knowledge and traditions stretching back generations. Then, suddenly, massive impacts from space trigger fires, floods, and climate disruption. Coastal settlements drown as sea levels rise. Food sources disappear as ecosystems are disrupted. The survivors scatter, fleeing to high ground, to inland regions, wherever they can find refuge. In the aftermath, these survivors would have found themselves among hunter-gatherer populations who had also survived the catastrophe, but who lacked the accumulated knowledge of the destroyed civilization. The survivors would have had to adapt, to share their knowledge in ways that made sense to people with very different backgrounds and needs. Some knowledge could be transferred: basic agriculture, stoneworking, observational astronomy. Other knowledge might have been lost, specialized skills that couldn't be maintained without the supporting infrastructure and population of the original civilization. This scenario of catastrophe and recovery, knowledge, transmission, and loss, would explain several puzzling features of early civilizations. It would explain why civilizations seem to emerge relatively suddenly in several regions around similar times after the end of the Ice Age. It would explain the sophisticated astronomical knowledge apparent in many early cultures. It would explain the global distribution of flood myths and tales of antediluvian sages who brought knowledge to humanity. What exactly was the catastrophe that destroyed this hypothesized civilization? Hancock embraces the Younger Dryas impact hypothesis, suggesting that comet fragments struck Earth around 12,800 years ago. The impacts would have caused immediate devastation in the strike zones, massive fires from the heat of entry and impact, and injection of dust and debris into the atmosphere. This would have triggered short-term global cooling and darkening of the skies. More devastating would have been the secondary effects. If the impacts struck ice sheets, as proposed, they would have caused massive melting, releasing huge volumes of meltwater into the oceans. This would have disrupted ocean circulation patterns, particularly the Atlantic meridional overturning circulation that transports heat from the tropics to northern latitudes. The disruption of this circulation would have caused regional cooling, particularly in the North Atlantic region, triggering the Younger Dryas cold period. For coastal civilizations, the flooding would have been catastrophic. Sea levels might have risen several meters in decades, perhaps even faster during meltwater pulses. Coastal cities and settlements would have been progressively inundated, forcing populations to retreat inland. Maritime infrastructure, ports, fishing grounds, all would have been disrupted. Even after the main flooding ended, the Younger Dryas cold period would have made many regions difficult to inhabit, causing crop failures, ecosystem disruption, and resource scarcity. If such a catastrophe occurred today, with modern technology, global communications, and stored knowledge in books and computers, we could probably recover and rebuild. But for a civilization without writing, without metal tools, without extensive food storage systems, the disruption would be nearly total. Knowledge preserved only in oral traditions and practical demonstrations would be at risk when elders died and communities scattered. Techniques requiring specialized tools or materials would be lost when supply chains broke down. Yet some knowledge might survive, transmitted through myths, through symbols, through monuments built to encode information and commemorate the lost world. This is where Hancock sees the pyramids and Sphinx fitting into the story. They are, in his view, monuments built after the catastrophe, but designed according to plans or principles inherited from before it. They mark astronomical epochs, encode mathematical relationships, and serve as stone books, preserving knowledge that survivors wanted to pass to future generations. If true, what knowledge might be waiting to be discovered in these monuments? Hancock speculates about possible hidden chambers, particularly the legendary Hall of Records that psychic Edgar Cayce claimed existed beneath the Sphinx. While Cayce's readings are not considered reliable evidence by scientists, the idea of hidden chambers is not inherently implausible. The pyramids already contain chambers and passages that were sealed and hidden for millennia. Ground-penetrating radar and other remote sensing techniques have detected anomalies at Giza that might be additional voids or chambers. The discovery of the void above the Grand Gallery in the Great Pyramid, announced in 2017, demonstrated that even intensively studied monuments can still hold undiscovered spaces. That void was detected using cosmic ray muon detectors, which can penetrate rock and identify less dense regions. The void is large, comparable in size to the Grand Gallery itself, but its purpose remains unknown because accessing it would require destructive excavation through the pyramid's structure, which Egyptian authorities are understandably reluctant to permit. Future technology might allow non-invasive investigation of these spaces. Advanced imaging techniques, miniaturized robots that could navigate narrow passages, even artificial intelligence analysis of radar data might reveal more about what lies hidden within the pyramids and beneath the Giza Plateau. Each discovery raises new questions and potentially revises our understanding. Underwater archaeology represents another frontier where future discoveries might be made. The continental shelves that were exposed during the Ice Age and then flooded at its end remain largely unexplored. The technology for underwater surveying and excavation has improved dramatically in recent years, with sophisticated sonar mapping, remotely operated vehicles, and underwater excavation techniques. But most of the world's continental shelves remain unmapped at high resolution. If Hancock is right that Ice Age civilizations were primarily coastal, then their settlements should be discoverable beneath the waves. They would be deeply buried in sediment accumulated over thousands of years, but so are many land sites that archaeologists successfully excavate. The challenge is knowing where to look and having the resources to conduct systematic surveys of vast underwater areas. Some intriguing underwater sites have been discovered, including what appear to be stone structures off the coasts of Japan, India, and elsewhere. These findings remain controversial, with debates about whether they're natural formations or human-made structures, but they demonstrate that underwater archaeology is a frontier with potential for surprising discoveries. What would constitute proof of Hancock's lost civilization? Most fundamentally, a clearly identifiable settlement or city from the Ice Age period that shows sophisticated architecture, evidence of astronomical knowledge, and advanced organizational capacity. Such a discovery would need to be thoroughly investigated by professional archaeologists, properly dated using multiple methods, and validated by the scientific community. Artifacts showing advanced technology or knowledge, such as accurate world maps, sophisticated astronomical instruments, or writing systems, would also be powerful evidence. Short of finding such definitive proof, accumulating indirect evidence could build a stronger case. If multiple sites around the world showed similar architectural principles, astronomical alignments, or encoded knowledge from the same epoch, that would suggest some kind of common influence or contact. If genetic studies revealed population movements at the end of the Ice Age, consistent with dispersal of a civilization's survivors, that would support the narrative. If the Younger Dryas impact hypothesis gained wider acceptance and impact structures were definitively identified, that would validate the catastrophe mechanism. The implications extend beyond archaeology and history into philosophy and how we think about human potential and vulnerability. If a sophisticated civilization could arise during the Ice Age and then be nearly erased from history by a cosmic impact, it suggests that our own civilization is more fragile than we might like to believe. It suggests that we should take seriously the threat of asteroid and comet impacts and work to develop detection and deflection capabilities. This is one reason Hancock sees his work as having contemporary relevance beyond just solving ancient mysteries. At the same time, if humans were capable of developing sophisticated knowledge and creating remarkable monuments during the challenging conditions of the Ice Age, it speaks to human resilience, ingenuity, and adaptability in ways that are inspiring. It suggests that we have deeper roots and potentially more untapped capabilities than we've recognized. These are big ideas that inspire wonder and speculation. They're part of why Hancock's books and documentaries resonate so powerfully with audiences around the world. In an age when official narratives and institutional authority are increasingly questioned, when people have access to more information than ever before and can make up their own minds about complex questions, Hancock's work appeals to a desire to think independently, to question what we've been told, to imagine that there's more to the story. Whether Graham Hancock's specific theories about the pyramids and the Sphinx turn out to be correct or not, he has undeniably made an impact. He's drawn attention to genuine anomalies that deserve investigation. He's inspired people to look more carefully at ancient monuments and ask deeper questions about their purpose and meaning. He's funded and promoted research, including underwater archaeology and geological investigations. He's created a popular audience for archaeological and geological research that might otherwise labor in obscurity. Critics would argue that he's also spread misinformation, led people to false conclusions, and muddied the waters of legitimate archaeology with speculation that isn't sufficiently grounded in evidence. They worry that his work makes it harder for the public to distinguish between rigorous scientific archaeology and entertaining but unfounded speculation. Both perspectives have merit. The truth, as it often does, likely lies somewhere in between. Hancock asks important questions and points to real mysteries, but some of his answers are speculative and not yet proven. Mainstream archaeology has deep expertise and rigorous methods, but it can also be conservative and resistant to challenging its established narratives. What's needed, perhaps, is more dialogue and less dismissiveness on both sides. Mainstream archaeologists could engage more seriously with the genuine anomalies that Hancock and others point out, even if they ultimately conclude that conventional explanations are sufficient. Alternative researchers like Hancock could acknowledge more clearly where their evidence is strong and where it's speculative, and could work more closely with academic institutions when possible. The pyramids and the Sphinx aren't going anywhere. They've stood for thousands of years and will stand for thousands more. They will continue to inspire wonder, speculation, and research. New technologies will allow us to study them in ways that weren't possible when Flinders Petrie conducted his survey in the 1880s, or when Robert Schoch first examined the Sphinx in the 1990s. Underwater archaeology will continue to explore the drowned coastlines of the Ice Age. Satellite surveys and ground-penetrating radar will continue to reveal hidden chambers and anomalies. Perhaps future discoveries will vindicate some of Hancock's theories. Perhaps they will support the conventional chronology. Perhaps, as often happens in science, the truth will turn out to be something neither side fully anticipated. What seems certain is that the mysteries of Giza will continue to captivate us, and the search for answers will continue. Graham Hancock's journey, has taken him from respected journalism to the frontiers of alternative archaeology. He's been celebrated by millions of readers and viewers and castigated by academic institutions. He's been called a visionary and a charlatan, sometimes in the same breath. Through it all, he's remained committed to his quest, searching for evidence of a lost civilization and challenging what he sees as the overly rigid narratives of mainstream archaeology. The pyramids and the Sphinx stand as they have for millennia, their stones bearing witness to human ambition, ingenuity, and the desire to create something that will outlast us. Whether they were built entirely by the ancient Egyptians of the 4th dynasty using techniques and knowledge we still struggle to understand, or whether they incorporate elements from an even earlier time, designed by survivors of a lost civilization trying to preserve their knowledge, they remain among humanity's most remarkable achievements. Walking among these monuments, feeling the weight of the massive stones, seeing the precision of their construction, and contemplating the vast stretch of time they've endured, it's impossible not to feel a sense of wonder. Somewhere in these stones, in their alignments and proportions, in the way they interact with the sun and stars, may lie messages we've yet to fully decode. Somewhere in the story of how they came to be may lie insights into human history that would change how we understand our past. Graham Hancock believes those messages and insights are waiting to be discovered. He believes that beneath the sands, hidden in dimensions and alignments, encoded in myth and monument, there's a story that extends human civilization deeper into the past than we've imagined. A story of achievement and catastrophe, of knowledge preserved and knowledge lost, of civilizations that rose and fell long before recorded history began. Mainstream archaeology remains skeptical, demanding more evidence, questioning Hancock's interpretations, defending the conventional chronology while acknowledging that there's still much we don't know about the ancient world. The debate continues, sometimes heated, often fascinating, always returning to these silent monuments that refuse to fully reveal their secrets. Perhaps that's fitting. The pyramids and the Sphinx have been mysterious for as long as we've had records of people contemplating them. Herodotus wondered about them 2,500 years ago. Arab historians puzzled over them 1,000 years ago. Travelers and scholars have measured, studied, and speculated about them for centuries. They've inspired countless theories, some scholarly and some fantastical, all trying to answer the fundamental questions: who built these, why, and what are they trying to tell us? Those questions remain open, and as long as they remain open, people like Graham Hancock will continue searching for answers, pushing the boundaries of conventional understanding, asking us to look again at monuments we thought we understood, and to consider possibilities we might have dismissed too quickly. The desert wind continues to blow across the Giza Plateau, as it has for countless millennia. The sun rises in the east, where the Sphinx eternally gazes, marking the same horizon that ancient peoples watched, tracking the same celestial cycles that Hancock believes are encoded in these stones. The stars wheel overhead in their slow procession, the same stars that ancient astronomers observed from these grounds, the same constellations that may have guided the layout of these monuments. And we, standing here at this moment in human history, look at these ancient stones and wonder. We wonder what hands shaped them, what minds conceived them, what purpose drove their creation, and what messages they might contain. We wonder about the people who built them, whose stories these monuments tell, whose knowledge they preserve. Graham Hancock's contribution, whatever the ultimate verdict on his specific theories, has been to remind us that wonder is important, that questions matter, that the past may be stranger and more sophisticated than we've allowed ourselves to imagine. He's reminded us that we shouldn't be too confident in our narratives about ancient peoples, that humility in the face of the unknown is appropriate, and that the search for truth about our origins is a worthy quest even when it leads down controversial paths. The pyramids and the Sphinx remain, as always, waiting for new technologies that might reveal their hidden chambers, waiting for new evidence that might resolve the debates about their age and purpose, waiting for future generations who will bring fresh eyes and new questions to these ancient mysteries. They've waited this long. They can wait a while longer. In the meantime, we have the work of researchers like Hancock who dare to ask the uncomfortable questions, the geologists like Robert Schoch who examine the evidence with scientific rigor, the astronomers like Robert Bauval who trace the patterns in the stars, and yes, the mainstream archaeologists who maintain the importance of careful, rigorous investigation, even as they resist speculative leaps. All of them, in their different ways, are trying to read the messages in stone, trying to understand what these monuments tell us about who we are and where we come from. All of them are part of the ongoing human project of understanding our past. And perhaps that's what the pyramids and the Sphinx ultimately represent, not just the achievements of ancient builders, but the enduring human drive to create, to preserve knowledge, to communicate across the vast distances of time, and to leave something that will outlast our brief existence. As we close this exploration of Graham Hancock's theories about the pyramids and the Sphinx, we're left with more questions than answers. That's appropriate. The greatest mysteries don't offer easy resolutions. They invite us deeper, challenge us to think harder, to question more carefully, to remain humble about what we know and what we don't know. Whether Hancock is a visionary explorer uncovering forgotten truths, or a speculative theorist seeing patterns that aren't really there, is a question each person must answer for themselves. What's undeniable is that he's sparked conversations, inspired research, and reminded millions of people that the ancient world still has secrets to share, if we're willing to look, to question, and to wonder. The pyramids and the Sphinx stand in the Egyptian desert, monuments to human ambition and ingenuity, repositories of mystery and wonder. They've survived floods and earthquakes, wars and conquests, centuries of plunder and millennia of weathering. They'll stand long after all of us are gone, still silent, still mysterious, still waiting for the day when humanity finally understands the full truth of their creation and purpose. Until that day comes, we have the search itself. We have the questions, the theories, the debates, and the discoveries yet to be made. We have Graham Hancock and researchers like him pushing the boundaries of conventional thinking. We have mainstream archaeologists defending the importance of rigorous evidence-based research. And we have these magnificent monuments themselves, silent teachers offering lessons we're still learning to read. The search continues, the mysteries endure, and somewhere in the stones of Giza, in their alignments and proportions, in their relationship to earth and sky, truths about human history may yet be waiting to be discovered. Perhaps those truths will vindicate Hancock's vision of a lost civilization. Perhaps they'll confirm the conventional narrative. Perhaps they'll reveal something entirely unexpected. Whatever they reveal, it will be another chapter in humanity's ongoing quest to understand ourselves, our history, and our place in the cosmos. And that quest, that eternal search for knowledge and understanding, may be the most human thing of all. Thank you for joining us on this journey through one of history's greatest mysteries. If you found this exploration thought-provoking, please take a moment to like this video and subscribe to the channel. Share your thoughts in the comments below. What do you make of Graham Hancock's theories? Do the pyramids and Sphinx hold secrets we've yet to uncover? The conversation continues, and your perspective matters. Until next time, keep questioning, keep wondering, and keep seeking the truth hidden in the shadows of our ancient past. Good night.